exactly the nuclear chemistry chapter, which we were talking about. So as we talked about last time, nuclear chemistry is different a little bit in terms of like nuclear reactions versus chemical reactions. And really the main difference, as we talked about last time, is nuclear reactions are all about really what's going on there in the nucleus. It's about protons, it's about neutrons. And that's different than in chemical reactions where it's all about pretty much electrons, bonds being made and broken. So there's usually a lot more energy associated with nuclear reactions as a result of kind of playing with what's in the nucleus. Also, we do not see sort of the conservation of elements, as obviously protons are the most important in terms of what element you're dealing with. So because there's really no conservation of protons along the way, in a lot of cases, we do make new elements as a result of nuclear reactions. And that's different than in chemical reactions where we don't really touch anything in the nucleus. We don't touch the protons, so we always basically maintain sort of the elements that are involved. We talk about balancing nuclear reactions, and because of what I just said, basically we do balance nuclear reactions a little bit differently. What we're looking for is when we're all said and done, the mass number, when you add up all the mass numbers on the left-hand side of the arrow here, they need to equal basically all the mass numbers on the right-hand side of the arrow. And same thing with the atomic number. All the atomic numbers on the left-hand side of the arrow need to equal all the atomic numbers on the right-hand side of the arrow. Now, there's a few different ways that you might be balancing equations. You may be given something where maybe something is missing. And remember that if something is sort of missing in an equation, you do want to attack the atomic number first. And that's because I'll give you a number of protons, and a periodic table, right? You could go and pick the element that it is, and you'll know sort of what's missing. And then you could do all the sort of mass numbers afterwards. Now, when we talk about radioactive decay, if something goes through some type of radioactive decay or some type of emission process, gives off this type of particle, remember that those particles basically end up on the product side of the arrow, if you sort of give it to it in words. We do have some sort of nuclear reactions, which, for example, like an electron capture. An electron capture would be on the reactant side of the arrow. And also sometimes you just say something like we're bombarding a nucleus with like a neutron or something like that, then the neutron would be on the reactant side. So we have several types of particles that we talked about. There is the alpha particle, which is also helium is used. There is the beta particle, which also an electron symbol is used. There's also a positron particle, which also uses an electron. There's also protons, which uses hydrogen as well. There's also neutrons as a sort of symbol, and gamma particles. So there's a lot of sort of different sort of particles or symbols that are used in this equation. We talked about stability in a couple of different ways you could look at stability. Remember, N to Z ratio is one way that you could look at the stability. And if something is outside the belt of stability or valley of stability, then it will go through a decay process to try to get itself back to it. Again, if we're a little bit on the high end here of the belt of stability, it will try to bring the ratio down by going through a beta decay. For a little bit on the low end, it could do a positron emission or an electron capture, which both will give you the same thing. That will bring the ratio back up to something that's really acceptable. Also, even and even is really, in terms of protons and neutrons, the best situation for a particular isotope. That is where we see a lot of stable isotopes happening. The worst situation a lot of times is odd and odd for both of those things. There's only like 5 of them, I think, that are pretty stable in that sort of arrangement. So not very much that's happening in that case. We then talked about a decay series. And remember, in a decay series, Basically what happens is whatever you make out of the first decay process, say that was an alpha particle, decay, that guy then would go down and then go through the next way, where it's a beta decay or an alpha, and that guy would then go down and go through the next. And it will continue this sort of decay series until you do hit something that is stable. You can basically do it like we talked about, just like you were balancing equations basically, and just kind of write one equation after the next, and I'll give you everything. You can also do it more mathematically if you're dealing with just alpha and beta sort of emissions. For every alpha emission, you subtract 4 from the mass number and 2 from the atomic number. And for every beta, you basically add 1 back. So if you're perhaps just interested in what you get at the end, you could kind of do that again if you just have alpha and beta. Obviously, if you have some other type of decay, then you would have to adjust accordingly. And lastly, we talked about kinetics here of radioactive decay, and that all follows first order kinetics. And that again is our natural log of A equals our natural log of A naught minus KT, where the half-life is equal to the natural log of 2 divided by K. Again, in nuclear chemistry, they'll sometimes use N's here for nuclides instead of A's. Also, as we talked about, you really could use any unit you want in the both of those as long as they are the same. So it does not have to be molarity. You can use grams of grams, milligrams of milligrams. You use a rate of radioactive decay in each of them as well. A reminder that maybe more than we did in kinetics sort of chapter, we very often will use this half-life equation along with the integrated rate law to basically figure out K a lot of times. And this is what's known as the decay constant in sort of nuclear chemistry. It's the same thing as basically the rate constant. And also sometimes people use a different symbol for that, but you could just roll with the same sort of kinetic symbols we used before. Any questions on any of that stuff there? All right, so I think it's where we left off. So why don't you give us one to go? Radon 222 is a gas causing lung cancer and leaks into homes. It is produced by uranium decay. Assuming no loss from leakage, if there's 10.24 grams of it in the house today, how much will be there in 5.4 weeks? The half-life of radon there 222 is 3.8 days. So see what you come up with here. Okay, let's take a look at it. So again, the good thing about radioactive decay, if it is radioactive decay, there's no choice in terms of what type of kinetics you should be doing. It should be first order, so you automatically kind of know the equations that you need to use. So in this case, we are starting with initially here 10.24 grams. We are looking for how much will be there at the end. So we're actually looking for that guy. And the time in this case is 5.4 weeks. So again, just looking at our equation here, we're looking for that. We got that. We got that. We are, which is very common in these type of problems, missing the decay constant. But the other piece of information they gave us was the half-life. So we have the half-life, and obviously here, that is where we could get our decay constant. Again, if you're sort of thinking about what's going on in terms of the calculation, units of time are different here, which will create a problem, obviously, if you come into here with 2 different units. So you probably should do some type of conversion. I'm going to convert the weeks into days. So 5.4 weeks will be 1 week is 7 days, I guess, to go with. And that's going to get me how many days? And now my unit of time in both sort of the half-life and will eventually be the decay constant are both now into units of days. Now you don't have to do that. You could have converted this guy into weeks, the half-life into weeks, and did it that way. They both really should come out the same. At this point, I'm going to use my half-life equation and rearrange it. They basically swap places. The half-life and these two guys basically just switch. And that's going to give me the natural log of 2 divided by my 3.8 days. And that will get me here, natural log of 2 divided by 3.8. Gets me 0.1824. Again, the units here are reciprocal days. Now I could put it into my equation. Natural log of A is equal to the natural log of 10.24 minus 0.1824 reciprocal days times my 37.8 days. And again, as I mentioned earlier, that is the important part right there, that we get the same units for both of those guys. And that's going to get us here something 0.18. Actually, just take the whole number, 37.8. If you do over here, you get something like 6.894990. And obviously our natural log of 10.24, natural log of A. All right, so clean up the right-hand side there, going to get us minus 4.56869. Again, to get rid of the natural log on the left-hand side, we will again, I'll do it above, but you actually do it below there. We're going to E both of those. And if we do that, that is going to give us a final, not necessarily concentration, but in this case, it will be the same units as our original guy. So 0.01037, and these would be grams in this case. Yeah. Any questions on that one there? So the good news about sort of radioactive decay and kinetics is it's the same kinetics we did obviously in the very first chapter, and it's always going to be first order in those two equations that go with it. Any questions on that? All right, so in addition to sort of what we just found there, we could also use radioactive decay to do some sort of dating of how old something is, like radiocarbon dating, uranium-238 dating. And for example, here we could use for carbon a half-life of 5730 years. And basically, we will still use essentially uh, our kinetics equation. And in this case, we could be solving for time in this case to see how old something is. We also use uranium, which will decay down to some lead. And again, by how much lead is there to begin with and end with, you could also use the half-life there to kind of figure out how old something is. So once you give this a go here, an ancient skull gives 4.5 disintegrations per minute per gram of carbon. And this is actually a unit of radioactive decay. And what people always kind of mess up on sometimes is the C here is actually carbon, not Celsius or anything like that. And really the purpose of seeing the carbon there is that will tell us what half-life we need to use, which is the one we saw on the previous slide. We would want to use the half-life of carbon, which as we saw there is 5730 is what we would want to use there. If a living organism gives 15.3 disintegrations per minute per gram of carbon, how old is the skull? So once you give it a go, again, as I mentioned before, you can use in these A and A naught grams like we did in the previous one, molarity, and you could also use this as a rate of radioactive decay can go in there for those guys to see what you come up with. For A and A naught, you can use those radioactive rates of decay. So an ancient skull gives 4.5 and a living one gives 15.3. So I'm going to go with living as the initial there. So that seems good. Disintegrations per minute per gram of carbon. And obviously the ancient one would be maybe not so much living there. So this is going to disintegrations per minute per gram of carbon. We want to know how old it is. So in this case, we are looking for time. Here we are going to use our half-life here because we are missing from our equation our decay constant here. We're looking for this guy. We're missing this guy, but we do have these two guys. Once again, and as I mentioned, as long as these are same units, you should be in good shape. So rearranging our half-life here, natural log of 2 over k gives us k is equal to the natural log of 2 over 5730 years. Once again, we know to use that because this is disintegrations per gram of carbon. And that will get us here a decay constant of, call it 1.21 times 10 to the minus 4. These again are reciprocal years as our unit, as it is first order, so it should be 1 over some unit of time for the decay constant. That will give us the natural log of 4.5 is equal to the natural log of 15.3 minus our decay constant we just solved for and our time. Again, I'm going to subtract that to the other side and then afterwards divide that to the other side. So we're going to go natural log of 4.5, it equals, subtract the natural log of 15.3, it equals. And then we're going to divide it by negative 1.21 to the negative 4. And that's going to give us a time of 10114 years. Sig fig wise, maybe like 10100 years. So about 10,000 years old. Yeah. Questions on that there? And obviously, the units of years comes from the decay constant. Obviously, when we do this dividing step, it goes from the bottom to the top there, and that's how we get to our years. Why don't you try another one here? Uh, yeah. We'll use this one. Archaeologists have dated the civilization to 15,600 years old. If a living sample gives 20 counts per minute per gram of carbon, what would be the number of counts per minute per gram of carbon for a rice that's found on the site? So why don't you give that a go? Obviously here we're doing grams of carbon, so half-life still the same 5730 that we used in the previous. Natural log of A is equal to the natural log of A naught minus KT. And again, our half-life equation still the same. Once again, this is a different sort of, a very different sort of unit of radioactive decay, counts per minute per gram, again, of carbon here. That's going to tell us half-life like we used there, 5730 years. In this particular case, though, we're actually looking for the rate of radioactive decay at the end. So we are looking for A in this case. We have our living, which would be our initial, which would be 20 counts per minute. We know the time there is 15,600 years. So once again, here we are missing the decay constant. We could get that from the half-life, and it will come out the same as in the previous problem because it is the same number here. And I think we had 1.21 times 10 to the minus 4 reciprocal years. In this case, unit-wise, so we have years and years, so everything is good in terms of that. Again, you always want to be careful of that to make sure you do have the same units going on. At this point, we could kind of put everything in, give us the natural log of A is equal to the natural log of 20 minus our 1.21 times 10 to the minus 4 reciprocal years and our 15,600 years. Again, the years are going to cancel. And we'll clean up the right-hand side there. That's going to be a natural log of 20 minus our 1.21 to the minus 4 times 15,600 years. And we're going to get natural log of A is equal to 1.108132227. We're going to E both sides. That gets rid of the natural log over there. And we'll go 3.03. Now, the units here are going to be really the same as our initial. So this would be counts per minute per gram of carbon in this case here. Any questions on that? It does make sense, right? It is decaying over a period of time, which means it's not going to give off as much radioactivity after a lot of years. So our final counts per minute should be a lot less than what we started with, as it's gone through several half-lives at that point, or a lot of half-lives at that point. We have much smaller counts per minute. Any questions on kinetics involving radioactive decay? All right, so now what we're going to talk about is where the energy of fission comes from. And a reminder that fission is the process where you have an unstable sort of nucleus, and it will typically split off into two new nucleuses. It will also give off several neutrons, and with it, it usually will give off a lot of energy. And this can be a spontaneous sort of process where you have something that's unstable that will go through this sort of splitting process. You could also initiate it, as we'll talk about, by, for example, shooting a particle like a neutron at something that's stable, and it will then become a little bit unhappy you did that and unstable, and will go through this decay process. Now, what happens as it goes through the fission process is there is a slight difference in the mass of the nucleons and the mass of the isotope. And remember, the nucleons are pretty much what's in the nucleus, which is your protons and your neutrons. So this slight difference in mass actually does get converted into energy. And one way that you can calculate the energy is by using kind of Einstein's equation here, E equals mc squared. M in this case is what is referred to, as we'll talk about in a second, the mass defect. C is the speed of light, which is basically 3 times 10 to the 8 meters per second. So you could actually use this to calculate the energy that comes as a result of this fission reaction. This is what is sometimes referred to as binding energy, is that energy that comes from this sort of difference in the mass of the components that make up the nucleus and that of the isotope itself. As we talked about earlier, again, the comparison of, say, something like uranium-235, which goes through fission, it releases about 1.7 times 10 to the 13 joules of energy per every mole. If you think about some type of exothermic chemical reaction, it produces about 10 to the 6 joules of energy per mole, much lower in energy. And this is why, again, sometimes it is used in, say, nuclear power plants and stuff like that. It produces a lot more energy than, say, a exothermic reaction. So that mass defect, as I mentioned before, is the difference between the mass of the nucleus and the mass of the isotope itself, is that mass defect. You could calculate binding energy a couple of ways. You can use, as we'll see in just a second, E equals mc squared. You could also, if you want, these are a few different sort of conversions that are used. They're kind of based off of that equation, and you could almost sort of bypass using that equation if you want. You could kind of use these conversions. Now, there are two common units of binding energy, and the two common units are joules per nucleon or mega electron volts per nucleon. And these are two units that are used to represent nuclear binding energy. And nuclear binding energy is also a measure of stability. And it's also a measure of stability. And as we will see shortly, the sort of higher the binding energy is per nucleon, the more stable something is. So for example, if we had something like fluorine 19, we can calculate the nuclear binding energy. And let's go through this sort of calculation. The first thing we'd want to figure out really is, in this isotope of fluorine, which has an atomic mass of 18.9984 AMU. We want to figure out how many protons and neutrons it has. So obviously it has 9 protons because that's the atomic number. The number of neutrons in this case obviously is the mass number minus the atomic number, which is 10. So we could calculate the mass defect, which is that difference in energy between the nucleus and the actual isotope. And we could calculate that by taking the 9 protons and timesing it by the atomic mass of a proton, 1.007825 AMU. We could add that to our 10 neutrons, which are in the nucleus, and times it by the atomic mass of our neutron, our 1.008665 AMU. And then what we would do is actually subtract it from the atomic mass of the isotope, which is in this case 18.9984 AMU. And if we do that, that will give us our mass defect, which is in this case about 0.158, we'll round it there, 68 AMU. Now, at this point, once you determine the mass defect, which again is that going to get converted into energy, you do have kind of 2 options as to how to do it. So I'm going to show you kind of both options here so you can see I could do either one. You can go into Einstein's equation equals mc squared. In this case, the m is our mass defect. So we can put this in here and take our 0.15868 AMU. We could times it by the speed of light, which is 3 times 10 to the 8 meters per second. And that's going to get us here. Basically 1.43 times 10 to the 16. Now the units here that I have at this point are AMU, meter squared, second squared. And this actually does not equal a joule. What does equal joule is something that's very close to it that you may remember. A joule is equal to a kilogram, meter squared, second squared. So essentially, kilogram is what we kind of need to get up there to get that into a joule. And to do that, we can take our number we just got there and we can basically divide it by our friend here, Avogadro's number there, 6.022 times 10 to the 26th, not 23, because when I do 23, that is per gram. When I do 26, that is per kilogram. Yeah, so 26 AMU per kilogram. Again, it's Avogadro's number, just a few more digits to make it into kilograms versus grams. That will cancel out. And that's now going to give us the unit that we really want. And if we do that there, we will end up with 2.37 times 10 to the minus 11. Our units now are kilograms, meter squared, second squared. And that is the same thing as a joule, is basically what all that equals. So you can use Einstein's equation. You do have to kind of use Avogadro's number to the 26th, not 23rd, to put it into kilograms. And that will give you joules. As I mentioned before, a common unit of binding energy is not just joules, but joules per nucleon. And in this case, we would take this and divide it by our nucleon, which is 19 in this case. It is essentially the mass number, which is the protons and the neutrons. And if you do that, you will end up with a binding energy per nucleon of 1.25 times 10 to the minus 12 joules per nucleon. And if you wanted sort of the other unit, you can use that conversion that we saw here on the previous slide, right here, that there is basically 1.602 to the minus 13 joules in a mega electron volt. The joules would cancel in that case, and you could convert it into the other common unit of binding energy, which in this case would be 7.79. We'll call it 1 mega electron volts per nucleon. So this is one approach that you could take to get the binding energy per nucleon. Most of the time we do calculate it in the positive sort of version. You could calculate it in the negative version, and it just has to do with whether or not you are talking about putting the atom or the nucleus together, are you breaking it apart? So if you're breaking it apart, it'll be more like this here, which would be the energy put in, right? And if you were kind of putting it together, it'd be more of an exothermic process. It'd be the same number, just positive or negative. So we usually roll with the positive version here in this class in most cases, but you can sometimes see it as a negative value, and it just means obviously the opposite, kind of putting it together as well. Now, if you did not want to use Einstein's equation, you could have picked it up from here, where we had obviously our AMU, and you could have honestly just rolled with those conversions that we had on the previous slide. And we could use our mega electron volt, which is 931.5 mega electron volts per AMU. AMU would cancel. Take your 931.5 and times it by 0.15868 and get a bad error there. You hit the wrong number. Where is that number? Take that times 931.5 gets you 147.806 mega electron volts. You then, if you wanted to, could divide it by the 19. And you could have got this first, our sort of mega electron volt answer. Just slightly different because of rounding, but essentially 7.7. In this case, I got 7.9 mega electron volts per nucleon. And again, just some rounding as to the difference there. And at that point, if you wanted to, you could have used your joule conversion in the opposite way there. And that would have got you, obviously, I ran out of room, but I'll just draw the arrow and basically get you back to there as well. So you could take sort of the bottom approach more just to kind of the conversion factors. You could use Einstein's equation and kind of get there as well. Either question on that there. As I mentioned before, nuclear binding energy is a measure of stability. So the higher the nuclear binding energy per nucleon is, the more stable that nucleus is. And that's what we see in this graph here. The higher it is, and it's really iron 56 there at sort of the top, the more stable you're going to see in terms of that. So you could also use, in addition to, for example, the N to Z ratio, you could use the binding energy if you have that information to per nucleon to measure stability as well. And as you can see here, we got our iron, and then things will kind of go through fission or fusion to try to get themselves into that more stable area. So why don't you try one here? Calculate the mass defect and nuclear binding energy per nucleon and mega electron volts. Why don't we also do both just to be safe there? Joules per nucleon and mega electron volts per nucleon. Of carbon 16 has an atomic mass of 16.014701. So see what you come up with there. And obviously carbon is 6. Again, we want our protons and neutrons. So obviously our protons are going to be 6, as that's the atomic number. Our number of neutrons going to be our mass number, which in this case is 16 minus 6, which give us 10. We could calculate our mass defect first off by basically adding those guys together with the masses of each of those particles. So we got 6 protons at 1.00783 AMU. We're going to add it to 10 times the mass of each of the neutrons. We're then going to subtract it from the mass of the isotope here, which is 16.014701 AMU. This is going to give us our mass defect. That will be kind of converted into energy here. So 6 times 1.00783 plus 10 times 1.00866 minus 16.014701. Give us a mass defect of 0.1189, I'll call it. And at this point, again, you do have two options. You could use Einstein's equation. You could just use those conversions. So I'm just going to use the conversions at this point. So we'll go mega electron volts first. 931.5 mega electron volts per AMU. That will get us here times 931.5. About 110.74 mega electron volts. Remember, we want it per nucleon, which means we would take this and divide it by really the mass number, which is 16. And if we do that, that's going to get us something like 6.921 mega electron volts per nucleon. And since we want both of them there, we can also just use our conversion there, joules to mega electron volts. So a mega electron volt is 1.602 times 10 to the minus 13 joules. And that will give us our other unit if we wanted, which would give us something like 1.11 times 10 to the minus 12 joules per nucleon in this case, right? Any questions on that one there? So again, you can see you can kind of bypass Einstein's equation and kind of use those conversions to kind of get you there as well. All right, let's try one more here, I think. Calculate the binding energy per nucleon for iron 56, and iron is 26 on the periodic table there. Again, obviously, you can use the same masses for protons and neutrons we did in the previous one there. Well, here we go, put it up here so you can see it. 26. Again, here we got our protons and our neutrons. So we got 26 there for our protons, and this is 56. So 56 minus 26 will give us 30 neutrons. So again, our mass defect here, we got 26 times our protons, 1.00783 AMU. Going to add it to our 30 times our neutrons, 1.00866 AMU. Again, going to subtract it from the atomic mass there of this isotope, 55.93494 AMU. That will get us here our mass defect of looks like 0.5284 AMU. Again, you could either use Einstein's equation or again, just those kind of conversions. Since it wanted it, didn't really say, but we'll go with AMU. We'll go with mega electron volts per AMU. So 931.5 mega electron volts per AMU. That's going to get us into our unit here of 492.24 mega electron volts. Again, going to divide it by 56 in this case, which would be our number of nucleons, which is our protons and neutrons. And that's going to give us an 8.79 mega electron volts per nucleon. You obviously could convert it into joules per nucleon if you wanted to at this point. Question on binding energy here. Now, if we look at the binding energy we did for our sort of three examples here, we had 6.92, I think, here for our carbon. At 6.92-ish mega electron volts per nucleon for our carbon. And we had 7.91 there for our original fluorine, if I'm not mistaken. Here, we had on this slide, I think. Yeah, 7.79-ish. So if we look at the stability and the nuclear binding energy per nucleon for each of these three that we just did, 7.7-ish mega electron volts per nucleon. Out of all three of these, here our iron 56 would be the most stable based on binding energy per nucleon, as it's the highest. Here, that was the carbon one, I think, would be our lowest, and obviously our fluorine would be in between. And that's what we saw there on that graph. At the top of the graph in terms of stability was actually this guy right here, our iron 56. So again, you can use that as a measure of stability. The higher the binding energy per nucleon, the more stable that nucleus is. Question on that there. Okay. So nuclear transmutation is really the process, as I was mentioning earlier, that you could kind of do to really cause a fission sort of situation to occur. You could have a particle which has a charge, a magnetic electrical field, and basically use it, particle accelerator, and shoot it at a target. That's essentially how they make all those kind of man-made elements, if you will, like all the ones with the fun names like Californium, Berkelium, Einsteinium, all those kind of guys there. All the ones kind of on the bottom there of the periodic table. They basically take a stable-ish type element, they shoot some type of particle at it, it gets a little unhappy, and that is what produces things like our curium, our californium, our einsteinium as a result of this nuclear transmutation. Again, as you shoot it at it, it becomes a little unstable. It goes through a fission reaction and produces those guys. And that's why they're sometimes referred to as the transuranium elements, as all those past uranium that are basically kind of made that way through shooting some type of particle. You can see sometimes it's a alpha particle, sometimes it's some neutrons that are shot at it to produce it. And in that process, when you do something like that, as you can see here, you shoot a neutron at a stable sort of uranium, becomes a bowling pin, not happy, and will split off into these new nucleuses. And again, will also produce some neutrons as a result of this splitting. In addition, the energy component that is produced as a result of this is pretty good. And as we've been talking about, much higher energy output per uranium than, for example, you would get at one combustion of coal, which is times 10 to the 7. The comparison there is in a traditional sort of power plant versus, say, a nuclear power plant. In a traditional power plant, they use coal, and they basically do a combustion of coal and use the energy for there to kind of run the power plant. In a nuclear power plant, they use uranium, and you can see you got a lot more energy per mole than you do through just basically burning coal. Now, when these things go through this sort of fission reaction, you don't always necessarily always get the same two products that are formed, but there is certain common ones that come across a lot with certain mass numbers that occur. This fission reaction is the reaction that's used in a power plant and also, for example, like in a traditional sort of nuclear bomb. And what can happen in this type of reaction, this fission reaction, is it can make what is sometimes referred to as a nuclear chain reaction. And a nuclear chain reaction is basically this fission reaction that basically just keeps going and just kind of keeps going, is self-sustaining. Is able to do that because it has what is known as the critical mass of something like uranium. And if you have the right amount of uranium, pretty much this reaction will just continue to kind of grow. And because this fission reaction involves, for example, a neutron to kick it off, Every time it goes through the fission reaction, it creates a lot of more neutrons here, which can keep this reaction going and going and growing again, sort of exponentially as it goes there. As it goes through each of these processes, as it's kind of growing, it's obviously creating a lot of nuclear products that are very radioactive. It's also giving off a lot of energy. One way that you could kind of control that is to keep a non-critical amount of something like uranium, and that will not allow this reaction to sort of just keep kind of growing out of control, and it will kind of keep it in control. That's sort of the idea here in a sense of this picture of a bomb. They have a subcritical amount of uranium there and over here separated from each other. But when this thing hits, the explosion will basically connect the dots, if you will, and basically fill in that wedge. And at that point, you will then have a critical mass of, say, uranium, and that will then allow this chain reaction to go. And obviously, not great things happen in that case. Obviously, a lot of energy, a lot of radioactive byproducts are released. Now, as I mentioned before, it is the same reaction, the fission reaction, essentially, that is used in a nuclear power plant. And how all power plants pretty much work is you usually have some water and you heat it up. And as you heat it up, you create some steam. That steam goes out to the turbines and to the generators, and then you get lights basically and stuff. And that's basically how both a traditional power plant works and a nuclear power plant works. The difference is the heating aspect of the water is different. In a traditional power plant, coal is used and through that combustion reaction. And obviously, uranium is used in a fission reaction in a nuclear power plant. So here's sort of a schematic of a typical nuclear reactor. They have a big thing of water. They have over here kind of where the radioactive part of the process basically occurs. They have some water that's fed in a tube that goes up and around and back around. And basically, they do the nuclear sort of fission reaction over here. The result of that is it's going to heat this water in this tube really, really hot. And that's going to cause the water in the secondary tube to start to evaporate. And that is the steam that will go out to basically use to power everything. They use what is known as fuel rods to do this. And fuel rods are like eraser shaped size pellets of uranium that go through that fission reaction that continues on to do that. Typically speaking, a lot of times these power plants would be by a big part of water. And that's because when you have steam, you can then cool it back down, get your water, and kind of keep this process kind of going in a cycle. That's why around us, right over there in San Onofre off the 5, right, is our nuclear power plants over there. Not working, I don't think anymore, but that's where they were. And they're by a big body of water and stuff like that. If you're sort of inland and you don't have a big body of water, a lot of times they would build nuclear power plants with really big, what they call cooling towers, which has a lot of water in it to kind of do that process for it. So if you ever driven to Arizona off the 10, over there in Palo Verde, they have the nuclear power plant. And obviously there's no whole big ocean right there, but they usually have certain cooling towers that is used to do that. Now, why does this fission reaction not go obviously all crazy in a sense? It's because they have some safety measures that they use when they do this type of reaction. They use a non-critical mass of uranium. So that would allow it not to go sort of out of control, the reaction, and make a chain reaction. They also have what are referred to as control rods that they have inserted in the nuclear part of it where it's happening. And these control rods are kind of soaked with cadmium. And cadmium's a good neutron absorber. And that's really good because if you think about how this reaction begins, it pretty much begins with a neutron kicking it off. Neutrons are also made as a result of this fission reaction. So with those control rods in, what they do is they kind of take out some of the neutrons from the reaction, and that also keeps it relatively under control and stuff like that. Obviously, good and bad with both. burning coal, right, does produce a lot of pollutants. Also, to get the coal, kind of ruins some of the land to kind of mine for it all. But also, nuclear power plants clearly makes a lot of radioactive waste, a lot of products as a result of it that's radioactive for a very, very long time. And also, it brought up the ideas, right, for a lot of years of kind of where do you put all that waste? Nobody wanted the waste near them. But they dug a big hole in Nevada now. That's how the lights stay on over there by Vegas. And I think they're starting to use it in the last several years. But for a lot of years, they would actually keep everything sort of on site because they couldn't travel it or move it around and stuff like that. A lot of our nuclear reactors are really not functioning anymore because it's too much money to kind of put it up to code these days. Um, but there's some good and bad with each of them. Part of the process of the fission, when you make those products that are sort of made as a result of those fission reactions, those are sometimes referred to as spent fuel. And spent fuel are the radioactive products that are made as a result of a fission reaction, which, as you can see here, part of the problem and part of the issue is this is how long you got to kind of keep these things stored until maybe, it drops down to not being so hazardous. And that is a lot of years, like 10 to the 3 years or however many years that may be. It's a lot of years of storage. And like I said, who keeps an eye on it, who watches it, where they put it is sort of a problem with that as well. Now, fusion, on the other hand, is a little bit different than fission. Fusion is the process where you take basically two smaller nuclei and make one bigger one, right? So two smaller guys make a larger one, two smallers make a larger one. This happens though at extremely high temperatures, like you're on the sun type temperatures, very, very high temperatures where this occurs. This is also why it doesn't usually occur typically under normal temperatures. You got to have that really extreme sort of temperature for it to occur. That's why all those movies, they want the guy that does cold fusion because obviously much better than trying to do it with the high temperature. As we talked about throughout this chapter, we do also use radioactive isotopes in medicine. And clearly, one of the advantages of radioactive isotopes, not only in medicine, but just in research as well, is it will do the same chemistry, for example, in your body as, the one that's non-radioactive element will do the same chemistry as the radioactive element. They both will basically do the same thing. So, for example, they could use something like sodium-24 as a blood flow tracer, iodine 131 for thyroid glands. And obviously, as you can see here, some brain imaging with iodine 123. They basically follow the radioactivity. So wherever that radioactive version of that element ends up, it will basically highlight those areas and give you some imaging. They've also, over the years, right, have implanted radioactive sort of pellets and tumors and stuff like that to try to shrink them. Here's again an example of a bone scan using technetium 99. Again, it will just highlight those areas. In, say, a regular research, if you're doing something like with a protein that involves maybe like a copper protein, you could use a radioactive version of copper, and you can basically follow where copper was throughout the whole sort of process of your purification of your protein by following the radioactivity. One of the things that you use a lot, if you ever do use radioactivity, in addition to maybe the ring and the badge that we talked about earlier, is a Geiger counter. And a Geiger counter will basically measure the radioactivity. It has a wand that basically will kind of make a sound, and a little needle will go up and down depending on where it's at in terms of how much. Makes a really loud sound, then that's a lot of radioactivity. If you hold up a Geiger counter just to the air, it will go off, not really loudly, but it will make some noise because there is background radiation. But typically, if you're working with radioactivity at the end, after you clean up, you usually use your Geiger counter, kind of go around and make sure you didn't contaminate the whole entire place and everything's sort of safe to work with. There is some biological effects of radioactivity or radiation on people, and it is based on, for example, a REM, which is a man equivalent. There is a factor and is based on the type of emitter it is. If you remember from earlier on, gamma rays and beta rays penetrate very far through lead and also your tissue as well. as opposed to alpha particles, which don't go as far. So a rad is your radiation absorbed dose. You could times it by Q, and you have a lot less timesing there because they will basically penetrate your tissue a lot more than, say, if you were working with something that's an alpha emitter, you maybe get a little bit more exposed. We do again have background radiation, as I mentioned, through all kinds of things, air travel. If you live near nuclear waste, ground and surroundings will give us some exposure, X-rays as well. And that is drawback.